There is another way that we can relate the rate to the concentrations of our reactants, and we're going to determine that by experiment. So what we do on these experiments is we hold one of our reactants constant, and then we see how, and we change the concentration of another reactant, and we see how the initial instantaneous rate is changed. Then we hold the other reactant constant and change the concentration of the one we held constant before to see how the rate changes, and then we can see the impact that each one has. So in this first one, we're holding NO2 minus constant. So nitrite is being held constant. So we're seeing how ammonium affects the rate. And in this bottom set, we're holding ammonium constant. So we're seeing how nitrite is affecting the rate. We know that each reactant has an impact and is related to the rate. So we can get this new rate law relationship where we say the rate is equal to some constant times by our reactant. In this case, we'll do both reactants, NH4, to some exponent times by the other reactant times a different exponent. And what we want to do is solve to find out what are these exponents, in which way are the concentrations impacting our rate. So if we do experiments 1 through 3, we're going to be seeing the effect of ammonium. So if I do rate 2 over rate 1, let me just show you what that will do. So if I do the rate 1, or let's do 2, 2 equals some constant times NH4 to the X, and NH4 2 times ammonium or nitrite to the Y, and this will be 2. Divided by, we'll do the rate of 1 equals, okay, and then NH4, that concentration of ammonium over X times nitrite of that concentration to the Y. Now, in this 1 through 3, nitrite is going to cancel out because it's the same number. The rate constant, well, you don't know what that is quite yet, but then this constant K will also cancel out potentially. So what we'll get is that the rates over each other are equal to ammonium to the X of the second condition over the first condition. So going back up, we end up getting rate 2 over 1. We can do any of those three and we should get the same value for X that we're trying to solve for, so that relationship. So rate 2 equals 10.8 times 10 to the negative 7. It's this one here, molar per second. Rate 1 is 5.4 times 10 to the negative 7. And that equals ammonium concentration 2, so 0.02 to the X over 0.01 to the X. So this whole thing is raised to the X power. So notice I have this value, the rates relationship is doubled. So 10.8 times 10 to the negative 7 divided by 5.4 times 10 to the negative 7 is 2. And that equals 0.02 divided by 0.01, which is 2 raised to the X. So the X value that makes this equation true is 1. So our X is 1. So we'll talk about what that looks like later. Now let's see how nitrite affects the rate. So here we have, so now here ammonium is staying constant. And so when we do our rates, we'll have our nitrites to the Y. And nitrite concentration will do 5 over 4. So we'll have rate of 5, which is 21.6 times 10 to the negative 7, divided by 10.8 times 10 to the negative 7. That equals nitrite in 5, so 0.0404 divided by 4, which is 0.0202, and all of that is to the y. So here we have the rates are doubled. That equals the concentration, which 0.04 over 0.02 is 2 raised to the y. So the order, or the y value for nitrate, is also 1. So if we put that together, our rate law, which shows the relationship between the rate and the concentration, so not the change of concentration, but the actual initial concentrations for the reactions, is the rate equals K, some constant, times ammonium to the 1. We can put the 1, but we don't have to, times nitrite, also to the 1. So the general, for this reaction, A of A plus B of B goes to C of C plus D of D. We can relate the rate by the change in our concentrations over time, or I can relate it by the rate law, which says the rate is equal to a constant times A, our reactant, to the X, and our other reactant to the y. And we can have more than 2, less than 2 reactants. We could have, and this X and Y is showing that those exponents are the reaction order, and this is not related to the stoichiometry. This is experimentally determined. So X and Y are experimentally determined. Okay, so the order for each reactant in this case is 1, because we have a 1 on each of these. And the reaction is second order overall, because if I add up each of those, I get a 2. So the total exponents add up to 2 for the overall reaction order, and the K value is our rate constant. It is temperature dependent. And we can get it, and it's going to be related to the activation energy, which we'll talk about later in a lot of detail. Okay, so like I said, the order of the reaction must be determined experimentally. Notice we saw that data. It's not related to the balance equation. Sometimes it works out like that, but a lot of times, and that's just a coincidence. So here I have this reaction of dinitrogen pentaoxide. The rate law that was determined experimentally has it being first order. Here I have hydrogen and iodine reacting to form hydrogen iodide, and that is first order with both. And then here we have this carbon-hydrogen compound with chlorine, and chlorine reacting to form carbon tetrachloride and hydrogen chloride gas, and that is 1.5 order total. So those are fun. The rate constant tells you how fast basically the reaction is happening. When K is greater than 1 billion or higher, the reaction is fast. If it's less than that, then it's slow. Okay, so let's look at this reaction here. Here I have A plus B goes to C, and the rate law is third order overall. So I have in this first one, A is red and B is purple. So here I have 5 A's and 5 B's. Here I have 7 A's and 3 B's. And here I have 3 A's and 7 B's. So rank these mixtures in order of increasing rate. So I'm going to do 1, 2, 3. So rate equals K, and then A to the first. So in 1 is 5 to the first, and then B to the second. So 5 squared. So I get K to the 125 or K times 125. Okay, for this next one, I'm going to have rate equals K. Now A is 7 and B is 3 squared. So I have 9 times 7, so K times 63. My last one, I have K. Now 3 times 7 squared, 49 times 3, and that is K times 147. So the one that's happening faster has a larger value, so it is number 3 is the fastest, and then 1, and then 2. So now pretend it's A squared times B. So that's going to basically just switch these two around. So its second is still going to be the middle. Since the order is just switched on how we, which is getting squared. So now 2 will be the fastest and 3 will be the slowest. So 2 is the fastest, 3 is the slowest, so E. And now with the rate being each to the first order, rank the mixture. So I have rate equals, so for 1, I have K times 5 times 5, so 25K. 2, K and 7 times 3, so 21K. And then 3 rate equals K, and now 3 times 7. So that is also 21K. So it's going to be 2 and 3 are the same, and those are both less than 1. Okay, so we're going to be using these reactions that we looked at earlier. Let's figure out the overall reaction order for 14.9 and 14.11. So 14.9 is K times N2O5, and that's just to the first, so the overall reaction order is first. Now for 14.11, I have K times CHCl3 to the first, and then Cl2 to the 1/2. So the reaction order is 1.5. What are the units of the rate constant for the rate law in 14.9? So what we want to do is solve for it. So I have a rate equals K times N2O5 to the first. Now units of rate are always going to be molar per second. Whoops. We don't know what K's units are, and then units of concentration are molar. So I'm going to find molar, get molar by itself. I'm going to divide by molar on both sides. So molar cancels out. So units for K is 1/seconds in this case. Now for 14.11, I have rate equals K, and then this reactant to the first. So again, rate is, molar per second. K, we're finding. Now this is molar and times molar to the 1/2. So what I get here is molar per second equals K times molar to the 3/2. So I'm going to divide by molar to the 3/2. So what I end up getting is, so that's going to cancel out now. So what I have is molar to the 2/2 divided by molar to the 3/2. When I divide, I'm subtracting, so do minus 3/2. So I end up getting molar to the -1/2. I can put some resources for those who need some exponent math help, because it is like a math skill that you learn. So feel free to look into that and ask for it, because I will be glad to help with that. And then this is all divided by seconds, so times inverse seconds. So molar to the -1/2, molar second to the -1. So we have A. reaction order of the reactant H2 in 14.10. H2 just is 1, so reaction order of 1. And the rate constant in 14.10. So I have rate equals K times H2 times I2. So rate is molar per second equals K. I have molar times molar, so I have molar squared. So I'm going to divide by molar squared. Divide by molar squared. So that molar cancels out, and then I get K units is inverse molar inverse seconds. And you can either do it like this, or you can do 1 over molar seconds. Either one. Okay, and for our last one, we're going to find the rate law for this reaction. So I have A plus B goes to C, and I have 3 different variables. So I'm going to find the rate law, the rate constant, and the rate at a certain concentration. So let's figure out, we're going to need to get A isolated and B isolated. So let's write the overall rate law here. Rate equals K times A to the X and B to the Y. And remember, if I want to get A isolated, I need to have B cancel out. So I'm going to find 2 experiments where B is the same. 1 and 3, those are the same. So I can use those to find out how changing A impacts the rate. So I'm going to have rate of 3 over rate 1. It doesn't matter, but I'm doing it such that I have a bigger number divided by a smaller number. That will give me an integer rather than a fraction. So I'll have 16.0 times 10 to the negative 5th divided by 4 times 10 to the negative 5th equals K divided by K. And then I have A at 0.2 to the X divided by 0.1 to the X, and then I have 0.1 for B to the Y over 0.1 to the Y. I'm not going to do that for the next one, but I just want to show you those cancel, K's cancel. So then I end up getting 4, so those 2 over each other equals 0.2 over 0.1 is 2 to the X. So in order to make this 2 squared equals 4, so X equals 2. So now I can go up here and erase and put a 2 in here. Ooh. Okay, now let's find a place where B is isolated and A cancels out. So if I look at A, 2 spots where they are the same is 1 and 2. So I'm going to do rate 2 over rate 1, and that's going to equal 4 times 10 to the negative 5th over 4 times 10 to the negative 5th equals, and now I'm not going to do the K's and the A's, I'm just going to do B. So now B for experiment 2 is 0.2 divided by 1 is 0.1 to the Y. So 4 over 4 is 1, those are cancel out to 1, equals 2 to the Y. So when we have something we need it to equal 1, Y is going to equal 0. So now I'll have for my thing here, B is 0. So my rate law, well, is this. So since B is to the 0, I can actually just erase the whole thing, and that's my rate law. So now I'm going to find the rate constant. It's a new color. So for the rate constant, you can pick any of the experiments, and then we're going to solve for K. So I'm just going to do 1. Sounds straightforward. So rate equals K times A squared. So rate is 4.0 times 10 to the negative fifth molar per second. And I'm going to want to write my units so I can solve for that as well. Units of K times A. Now A in this case is 0.1, and we're going to, whoops, I lied. I want to put 0.1 molar, and I want to square it. So now 4.0 times 10 to the negative 5 molar per second equals K times 0.01 molar squared. I'm going to divide by 0.01 molar squared. And I get my K value equals 4.0 times 10 to the negative 3 inverse. So my molar on top is going to cancel out one of these, and so I have inverse molar inverse seconds. So when I write my full rate law, I'm going to write rate equals my rate constant. I'm going to put the actual value, 4.0 times 10 to the negative 3 inverse molar inverse seconds times A squared. So this is actually really cool because now I can predict what my rate is going to be with any concentration of my reactants. So in the problem, it wants to know what's the rate when A, concentration of A equals 0.05 molar and B equals 0.1 molar. Now we know B doesn't have any impact because it's not in a rate law. So let's find out what the rate is. So rate equals 4.0 times 10 to the negative 3 molar inverse second times A is 0.05 squared. So now, and don't forget my units, molar. So now when I plug that in to my calculator, I end up getting that my rate equals 1 times 10 to the negative 5. 1.0 times 10 to the negative 5 molar per second. So that is how we can relate our rates. So remember rate, we find our rates from our change in our 1 over our stoichiometric coefficient times my change in my reactant concentration over time. When I plot that instantaneous rate, so this is experimental, we would plot that change. Then I would take this data and plot it at different concentrations to see how the rate is impacted, and then I can find the rate law based off of that info, like that. So it's all connected, and these are all different ways that we can see how the rate of a reaction is impacted by either concentration or at different times.